Hello, everyone, and welcome back. Last episode, we came across the notion of factorial. The factorial of a number n, an positive integer n, is simply the product of all numbers between 1 and n. So 1 times 2 times 3, up to n. In particular, 1 factorial is just 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1, 2, 3 is 6, etc. Also, by convention, we set 0 factorial to be 1. We will find out later why that convention is useful. For now, let's just remember that. Today, we will practice with the notion of factorial, and we will solve a version of the birthday problem from the first episode. This will be version 2. What's the probability that among your friends, 100 friends, let's say, among your 100 friends, some of them share a birthday among themselves. Some of them have a repeated birthday. So some have the same birthday. What do you think? 100 friends, 365 days in a year. So it's about 3 days per friend. So they can have all different birthdays. It's possible. Is it likely? Is it unlikely? Do you think in the birthday problem, the probability that your friends share some birthdays is likely or unlikely? Should it be like greater than 1/2, maybe smaller than 1/2? Think about it. What's your gut feeling? We'll find out. You'll be surprised. This problem has a non-trivial and non-intuitive answer. How do we solve it? As before, the trick is to pass to the opposite or complementary problem. The opposite. So suppose it's not happening what we would like. It's not true that some of the friends share their birthday. What does that mean? It means that all of these friends have different birthdays. That's a complementary one, right? So we would like to find the probability that all birthdays, all 100 birthdays are different. If we solve this one, if we find out that probability, we will just subtract it from 1 and get the answer to the original problem, because the sum of the probabilities is 1. Yeah, there are 2 options. Either all birthdays are different or some are repeated. No third option. Therefore, the sum of these 2 probabilities should be always 1. Okay, let's solve this problem. How do we do this? We do this by pretending that we're assigning birthdays to our friends. We do not know what their birthdays are, so maybe we're like a superpower who assigns the birthdays. And how many ways are there to do that? The number of ways to assign birthdays to your 100 friends. That's easy. There are 365 ways to assign the birthday to the first friend, obviously. Regardless of that, once we do that, there are still 365 ways to assign the birthday to the second friend. Once these are selected for any pair of birthdays, for friend 1, friend 2, there are still 365 ways to select the birthday of the third friend, and so on and so forth. So the ultimate number of ways to assign birthdays to 100 friends is this: 365 raised to the power of 100, a huge number. And we assume that all such assignments are equally likely. This is because we don't care. We don't know what friends' birthdays are. So each combination of every combination of birthdays it's going to be the same to us. It's going to have the same probability before we know it. So all birthdays assignments are equally likely. There is this many possible assignments, but what are the number of valid assignments? The number of the assignments, number of ways to assign birthdays, what we care about. The number of ways to assign, we care about all different birthdays, all different birthdays. So look at friend one. How many ways are there to assign birthday to friend one? Well, still 365. Now look at your friend two. How many ways are there to assign birthday to friend two? So it'd be different from friend one's. 364, because we can't assign the same birthday as for the first friend. Now let's look at friend three. We can assign any birthday except those that are already taken by friend one, friend two. That leaves them 363 possibilities, and so on. So we multiply these numbers for all the friends 100 times, and the last number in this list going down, if you think a little bit, will be 266. This number, this long list of numbers, is not very convenient to work with, isn't it? There is a nice way to represent it in mathematics using factorials. Let's do it. The product 365 times 364, 363, and going down is already looks like factorial, doesn't it? And factorial is the product of all numbers going down from n to 1, and this is a product of numbers going from 365 down. Unfortunately, this particular product, this one, doesn't stop at 1. It stops short of 1 at 266. So in order to represent as a factorial, let's pretend that it actually goes down to 1 all the way to 66, but it also goes like 265. I know this number is non-existent in that product, but just bear with me. Let's pretend we have all these numbers, 3, 2, 1 here. That's wrong. Of course, it doesn't, we can say it's equals to, because we multiplied. So let's correct ourselves. To correct this, we divide by what we multiplied by. 264, 3, 2, 1. Now this is correct. Now this is a true equality. And on the top, the numerator is simply 365 factorial. Now it's correct. The numerator is 265 factorial. And that is the number of valid assignments. This is the number of all assignments. Perfect. So what's the probability? The probability that all birthdays are different, because all assignments are equally likely, is just a ratio of how many valid assignments we have. That one. Over the number of all assignments, to 365 raised to the power of 100. And that's an answer. That's the answer. You can compute that. And I did. And this is approximately, so is it a small number or is it a large number? I think it's a very, very small number, actually. It's 3 times 10 to the minus 7. It was like 10 million, 3 in 10 million chance. Very, very small probability that all birthdays are different. Remember, this is the complementary problem. So the solution to the original problem, that some birthdays are shared, that there are friends with the same birthday, is 1 minus that. 3 times 10 to the minus 7, and which is 0.999997. 6 nines here. So it's an extremely likely that among your 100 friends, some will share a birthday. Not just likely, but it is beyond any reasonable doubt. Almost certainly it's true. You will probably, if you ask anybody on the planet, there will be 3 people, maybe 4 people, maybe something like that, who have ever seen this not happening. So for all of that, their transparencies are shared. And that's something non-intuitive, maybe. Good. So we solved this problem. But there is a catch. And the catch is here. It actually is difficult to put that in the calculator. If you put this in the computer, just like that, the computer will complain. The computer won't like that. So the big issue, the big problem here is that if you put 365 factorial in a computer, either a scientific calculator or MATLAB, it says it's infinity. What's going on here? It's not infinity, but the computer thinks it is. The computer thinks it's such a large number, it's such a huge number that it won't hold it. It would just can't really calculate that number. So how can we do that? How can we solve problems like that? Put this in the computer. And why? Is it really such a big number? Actually, it is. It is a big number because the n factorial, which is, remember, just a product of these two, innocent-looking product, it grows too fast when you let n grow. For example, 1 factorial is 1 and 2 factorial is 2, but 10 factorial is 3,682,800. And 20 factorial, I don't know what it is, but it's already unimaginable. And 365 factorial, even the computer cannot do that. So what do? How can this number be computed? The factorials are not such a good way to do that, unfortunately. And here we come to a very, very useful approximation to a factorial that people do like and use all the time. This is called Stirling formula, or Stirling's approximation. Instead of computing the factorial directly, you use a very good approximation, which reads like this: n factorial is approximately, I'll do it in 3 chunks, is approximately n to the power of n, and that's how it grows. It grows super exponentially fast. E to the n would be exponentially fast, and n to the n is super exponentially fast. But that is only the first part of the truth. This second correction is n divided by e. Well, so this is going still super exponentially fast. And one more correction to the truth is root 2 pi n times this. So this is Stirling's approximation, a beautiful formula that combines the notion of the factorial and the classical exponential rate and the classical constants e and pi in just one simple, beautiful formula. We will not prove this formula in this course. If you like, check out Wikipedia. If you are a calculus student, if you know enough calculus, you can derive it from Taylor's expansion. It's a very good, challenging exercise, but it's a rewarding one. Good. So this formula is actually computable. That can be put in the calculator. And here is how. Okay, so now let's take this formula and compute this expression using Stirling's approximation. So this, we are facing, okay, n is 365. That's how many days we have. K is 100 friends. So over here, right there, we have n factorial divided by n minus k factorial, that's 265 factorial, divided by n to the k. Okay, I just denoted n and k this numbers, and that's what we're about to compute. Okay, let's do it. Stirling's expansion, Stirling's formula. Let's do it. N factorial, that's root 2 pi n over e to the n minus k factorial, I'll move it down, will be root 2 pi n minus k n minus k over e to the k to the n minus k. Okay. And then there is n to the k. There's n to the k. I know it's ugly. Yeah. It's a little ugly formula, but it doesn't have factorials anymore. So this is a Stirling's approximation. The beauty of this formula is that things cancel. For instance, it's obvious in this formula that 2 pi will cancel, isn't it? 2 pi here and 2 pi will cancel, but that's not the main point. A lot of e to the n will cancel too. Do it by yourself. Just simplify this formula, cancel all the terms that will cancel, and you will get something like this. This is do it yourself project. Just cancel the terms and you will see it's true. Now in this formula, there is no factorials and the numbers are manageable, and that you can compute. So this is computable. And remember, n is 365 and k is 100. And if you substitute these values, that is how I actually got this number. That's how I computed it, not by directly computing factorials, but by doing Stirling's approximations on them. Okay, so in this course, in this class, this episode, we learned how to deal with factorials using Stirling's expansion and how they arise in probability problems. Stay with me for the next episode.